Start this video by beginning the discussion of section 7.4 of Dumb and Foot, which is all about properties of ideals. And I really want to highlight that there is one sentence at the beginning of this section that is really important and is easy to forget it's there if you go into section 0.4 looking for the statement of a particular result. So Dumb and Foot start by saying, throughout this section, R is a ring with identity, 1 not equal to 0. So this is potentially confusing because Dumb and Foot go to great lengths earlier in the discussion of rings to not assume that every ring has an identity. But for the material of this section, they really do want to assume that every ring has an identity. So later on, actually in the next lecture, I'll point out to you one of the things that we'll prove in this section is just false if R is not assumed to have an identity. Okay, so the thing that I want to talk about in this video is where do ideals come from? I give you a ring and I ask you to find a bunch of ideals. Well, what about the corresponding question for groups? I give you a group and I ask you to produce a bunch of subgroups. One thing you can do is take a bunch of cyclic subgroups. And then more generally, you can take a bunch of subsets A in G. And for each A, you have the subgroup of G generated by A. So we're going to start by talking about the corresponding construction for ideals. And it really is pretty parallel to this discussion of subgroups generated by subsets. Okay, so here we go. Let's let A be any subset of our ring R. And this parentheses A notation, this is going to be the smallest ideal of R containing A. This is called the ideal generated by A, just like the corresponding thing for a subgroup is the subgroup generated by A. All right, so we're going to use this notation for the smallest ideal of R containing A, but you can also make a similar definition for the smallest left ideal of R containing A or the smallest right ideal of R containing A. I don't have a special notation in mind for that. That's not going to come up in our setting so much because we really are going to focus on the case where either R is commutative or in cases like we saw MNR where MNR is not commutative, but we have this special class of two-sided ideals. Okay, so one thing that we're going to need in this discussion is exercise 18 of section 7.3, which is on this homework 7 that is due on Friday, which says if you just take an arbitrary collection of ideals, it can be infinite, and you take the intersection over all of those ideals, you get another ideal. So one way to say it is you have some index set X. It could be infinite, maybe not. And you have one ideal for each element in X. Then the intersection of all of these ideals is again an ideal of R. All right, so this is going to give us our first description of this ideal of R containing A. A is contained in at least one ideal because R is an ideal of itself. So A is contained in R. That's one ideal. So if we take the intersection over all of the ideals containing A, that's a non-empty collection of ideals. So in particular, whatever this intersection is, it's an ideal. And it contains A. And it's easy to see that if you have any other ideal containing A, it contains this intersection of all of the ideals containing A, because that ideal containing A would have to occur as one of the ideals in this big intersection. So what is that telling us? That's telling us that the ideal generated by A, the smallest ideal of R containing A, is the intersection of all of the ideals of R containing A. So let me just say, this is very similar to the first description we gave of the subgroup generated by A. It was the intersection of all of the subgroups of G containing our set A. So what did we do next is we talked about how to describe this subgroup generated by A in terms of words written in elements of A and the inverses of elements of A that have finite length. So the next thing we're going to do is give the corresponding description for ideals. How do you describe this intersection of all of the ideals containing A in terms of the elements of A? So I'll pause and erase, and then we'll start with that discussion. Now let's try to understand this ideal generated by A in a different way. So let's let RA be the set of all finite sums of elements of the form little r times little a, something in the ring times something in A. So written a different way, this is the collection of all the things that are of the form R1A1 plus R2A2 plus RnAn, where these Ri's are in the ring, these Ai's are in A, and n is a non-negative, or it's a positive integer. So you might wonder what happens if A is the empty set, and there are a bunch of good reasons to define RA to be equal to just the additive identity of R if A is equal to the empty set. I'll let you think about those. So you can make a totally parallel definition where instead of having RA, where you have something in the ring times something in A, you have AR, which is something in A times something in R, finite sums of things of that form. So A1 R1 plus AN Rn. So in both of these cases, it looks like what we're getting are linear combinations of things in our subset A where our coefficients live in the ring. Okay, one particularly important special case is when A consists of a single element, little a. So in that case, instead of writing RA, we often write R times the element, which is everything of the form R1 times A plus R2 times A plus Rn times A, where these Ri's are in the ring and n is a positive integer. So finite sums of things of the form something in the ring times our one element little a. But in this special case where A consists of a single element, we have R1A plus R2A plus Rna by the distributive law is equal to R1 plus R2 plus Rn times A, which this element, the sum of these Ri's, is another element of our ring. It's something in the ring times A. So in this special case, where our subset has one element, RA really is all of the things of the form something in the ring times our one little a. Totally parallel definition with multiplication on the other side. AR is all of the things of the form A times something in the ring. So I actually really like what Dummett and Foote do here, that they start with the general definition for a subset A, where you really have to take finite sums of elements of the form something in the ring times something in your subset. Because a lot of texts will start with the case where your subset has one element. And in that case, you really can think of your RA as something in the ring times something in A. You can kind of forget about this finite sums part. But in general, it's just not true that RA is the collection of all of the things of the form R times A, where R is in the ring and A is in your subset. That's generally not closed under addition. This is just like the discussion that we had around the product of two ideals I and J, where we're not just taking everything of the form something in I times something in J, but we really have to take finite sums of things in that form. So I like that Dummett and Foote do the general definition first before talking about the case where your subset is a single element, because in the single element case, you don't have to think about this finite sums bit. So yeah, so it's better, I think, to really emphasize this at the beginning. Okay, so moving on. What is true about these sets, RA, AR? Well, it's easy to see that if you take any subset A, RA is a subgroup of R under addition. So how do you see that? Well, the subgroup criterion. Just take one thing of this form and another thing of this form and subtract. So take X and Y and show that X minus Y still is in RA. And you can do that just by grouping together the coefficients of the AIs that occur in both of your elements. All right, so what else do you need? It's an additive subgroup of R, but it also has some additional structure. In particular, RA is a left ideal of R. So we need to show that it's closed under left multiplication by elements in the ring. So let's pick some elements in the ring, pick some elements in RA, and look at the product. So S times R1A1 plus 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 RNAN. We can just distribute and see that that's SR1A1 plus SR2A2 plus 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 SRNAN. And S times R1 is some element of the ring, and S times R2 is some element of the ring, and S times Rn is some element of the ring. So we're back in this form. We still have something in the ring times A1 plus something in the ring times A2. So this lands back in RA. So we have seen that RA is a left ideal of R. What is true about this left ideal? So this is really important. This is one of the reasons why Dummett and Foote emphasized at the beginning of the section that R is a ring with unity. Since 1 is in your ring, what is contained in RA, in particular, you have all of the things that are of the form 1 times A. So you get the entire subset A inside of RA. So if R doesn't have an identity, who's to say whether A is contained in RA or not? Okay, so why is that important? Well, we want to give another description of RA. Let's say J is any ideal of R that contains A. Okay, so certainly J has to contain all sums of the form something in the ring times something in A, plus something else in the ring times something in A, plus 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 Rn. Because it contains, I want J not to be an ideal in general, but let me just say that J is a left ideal. Right, so it's still true that J contains all of the elements AI, and every element is closed under left multiplication by elements in the ring. So it contains R1A1, it contains R2A2, it contains RNAN, and it's an additive subgroup of R. So it contains all these sums, R1A1 plus 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 RNAN. So in particular, if J is any left ideal of R that contains A, it contains RA. So what does that mean? That means that RA is some left ideal of the ring that contains A, and it contains every other left ideal of the ring that contains A. So RA is the smallest left ideal of R that contains A. So that is what we were talking about at the beginning of this video. So you can do everything entirely parallel for right ideals instead of left ideals and see that AR is the smallest right ideal of R that contains A. So I'll pause and erase, and then I'll talk about going from left ideals and right ideals to two-sided ideals. We have seen that RA is the smallest left ideal of R that contains A, and AR is the smallest right ideal of R that contains A. So what about two-sided ideals? A two-sided ideal of R that contains A, well, it must contain all of the elements that are of the form something in R times something in A times something in R on the right. And since it's an additive subgroup of R, it has to contain all finite sums of that form. So in particular, it has to contain everything that looks like R1A1 R1 prime plus R2A2 R2 prime plus 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 RNAN Rn prime, where these R1 R1 prime and all these other Ri's and Ri primes are just elements of the ring, and these AIs are elements of our subset A, and n is just some positive integer. So just like we have RA and we have AR, we're going to call this RAR. So now we can follow the same strategy as earlier and check first that this is a two-sided ideal of R containing A. It's easy to use the subgroup criterion to see that it is an additive subgroup of R. And then showing that it's closed under left multiplication by elements of the ring and also by right multiplication by elements of the ring just uses the distributive law in the same kind of way that we used it earlier. So it is some two-sided ideal. Why does it contain A? Because you could just pick R1 and R1 prime to be equal to the identity of R. So here again, it's important that R be a ring with unity. Okay, so now it's some two-sided ideal containing A. And just like we showed that RA is the smallest left ideal of R that contains A, we can show that RAR is the smallest two-sided ideal of R containing A. You start with any other two-sided ideal of R containing A, and you show, well, it has to have all the elements of the form RA, R prime. And since it's an additive subgroup, it contains all the finite sums of those things. So it is the smallest two-sided ideal of R containing A, but we already have a name for that. That is the ideal generated by A. So that is the intersection over all ideals in R that contain A. So just like in our discussion of subgroups, where we first described the subgroup generated by a subset A in terms of the intersection over all of the subgroups of G containing A, and then we described it in terms of words of finite length written in elements of A and elements and their inverses. This is what's going on here. We first see the ideal generated by A as an intersection of all the ideals containing A, and now we're seeing it in terms of finite sums of elements of a special form. Okay, we've talked about the left ideal of the RA, the smallest left ideal of R containing A, the smallest right ideal of R containing A, the smallest two-sided ideal of R containing A. If R is commutative, these are all the same thing. So in most of our examples, RA, AR, RAR are all the same, so you won't have to think about multiplying both on the left and on the right by elements of the ring. But you should be aware that really when R is not commutative, understanding the ideal generated by a subset A really is a more complicated looking object. And one example that really hammers that home is when A consists of a single element. So we already saw if you have some A in the ring, you can take your set capital A to just consist of that little a. And RA is, using the distributive law, everything of the form something in the ring times little a. AR is everything of the form little a times something in the ring. Like here, you don't have to think about these finite sums of elements of this form because of the distributive law. But RAR, the smallest two-sided ideal of R containing this element little a, is really not, in general, just all of the things of the form something in the ring times A times something in the ring. Because this set is not usually closed under addition. It really is a lot like this case of understanding the product of two ideals as finite sums of something in I times something in J, not just the collection of something in I times something in J. So in the case when R is not commutative, it really is important to think about RAR as finite sums of elements of this form, RAR prime. So this is one instance that's really showing how ideals in non-commutative rings are more complicated to understand than ideals in commutative rings. You want to find an ideal in a commutative ring? Pick your favorite elements, A, and just take all the things of the form something in the ring times A. In a non-commutative ring, much more complicated to see what does this set look like. Like R1A, R prime plus R2, or R1A, R1 prime plus R2A, R2 prime plus RNA, Rn prime. It's much harder to get a handle on what that object consists of. Okay, so now, given all of this discussion, we can make two really important definitions. First, an ideal is called a principal ideal if it is the smallest ideal of the ring containing some element A. So if you can write it as the ideal generated by some subset of the ring where that subset has one element. So in particular, in the case where your ring is commutative. An ideal is principal if it's one of these, if it's everything of the form something in the ring times one element. Okay, along with that, I is finitely generated if maybe it's not the ideal generated by some subset A where that subset is one element exactly, but if I is the subset generated by A for some finite subset A in the ring. So it's just like the definition of what it means to be a finitely generated subgroup of a group. Okay, so I'm going to pause and erase, and I'll give one simple example where we can understand what all of the ideals look like. And then in the next video, I'll talk about two more complicated examples. I'll show you an ideal in a ring that is not principal, and then an ideal in a ring that's not even finitely generated. Let's talk a little bit about principal ideals. And let's look just at the case of a commutative ring R. So in this case, if we have the principal ideal generated by A, then what does it mean for B to be in that ideal? It means B is equal to something in the ring times A. So this is where it's really important that R is a commutative ring. It could be that if R is non-commutative, B is in the ideal generated by A, but B is just not equal to something in R times A times something in R, right? It might really be a finite sum of elements of that form that's not equal to one element of that form. So, okay, let's just think about the case of a commutative ring here. So what does this look like, though, for integers? This looks like what it means for B to be a multiple of A, right? So we're going to use that same terminology. We'll say that B equals RA. That means that B is a multiple of A, or equivalently, that A divides B in R, that there exists some little element, little r in R, so that R times A equals B. That'll mean A divides B in R. So one more thing about principal ideals. If B is in the ideal generated by A, then, okay, if you think about what are the elements of the ideal generated by B, then it's clear that the entire ideal generated by B is contained in the ideal generated by A. And the converse of that statement, if the ideal generated by B is contained in the ideal generated by A, then again, because your ring has an identity, the element B is in the ideal generated by B. So in particular, the element B is in the ideal generated by A. So what are we seeing? B is in the ideal generated by A if and only if the ideal generated by B is in the ideal generated by A. Okay, so this statement here, this is true even when R is non-commutative, if you just think about what the elements look like. All right, so the last thing I want to do in this video is talk a little bit about just the simplest examples. So the trivial ideal in a ring is always principal. It's the ideal generated by just the additive identity. That's easy to check. If you think about, what the ideal generated by 0 looks like, that's all you get. R itself is a principal ideal. Again, now it's important that your ring R contain a multiplicative identity. The ideal generated by that identity, well, it certainly contains everything of the form something in the ring times 1. But that's everything in the ring. That's all of R. So the ideal generated by the multiplicative identity is the whole ring. Okay, so now let's look at a particular example. Let's say R equals Z. We know already that every ideal is of the form NZ, because that's what all the additive subgroups of R look like. These ideals are all principal. NZ is the ideal generated by N, and it's also the ideal generated by negative N. This is true if you have the trivial ideal, then N and negative N are the same. They're both 0. But otherwise, you have these two generators to describe the principal ideal NZ. Okay, what about the ideal generated by 2 elements? What if your subset A has 2 elements, N and M? So what is the ideal generated by N and M? Well, it's all finite sums of things of the form something in the ring times something in this 2-element subset. So it's grouping everything together. You can think of this as the set of all things that are n times an integer plus m times an integer. So this is some ideal in Z. And we know that every ideal in Z is principal. They're all of the form nz for some n. I don't want to use n, the same letter again here. So this is equal to dz for some integer d. Which one? Well, one way to think about it is this set, the ideal generated by n and m, everything of the form n times an integer plus m times an integer, this is the sum of the ideals nz and mz that we saw earlier, right? It's just something in the first ideal plus something in the second ideal. So what is the ideal generated by n and m? Well, it's the same thing that this ideal was. So it's the ideal generated by the greatest common divisor, GCD nm z. So what are we seeing in this statement, that the ideal generated by these two elements is the sum of the ideals generated by each one of those elements? Well, more generally, if you have two subsets of R, in the case where R is a commutative ring, this is what allowed us to like group everything together to just think of this as n times an integer plus m times an integer. So in the case where you have a commutative ring, the ideal generated by A and B is the sum of the ideal generated by A and the ideal generated by B.